In this video, we discuss symmetry and how to test an equation for symmetry. Sometimes graphs of equations can have symmetry in the plane. There's three types of symmetry in the plane. Number one here, x-axis symmetry. What does this mean? It means that when you rotate the graph 180 degrees about the x-axis, the graph appears the same as the original. In this case, it's said to have x-axis symmetry. Look at number two. This graph here, now this graph is the curve here, going up. And when I rotate this graph 180 degrees about the y-axis, the graph appears to look the same. So therefore it has y-axis symmetry. If I tried to rotate it 180 degrees about the x-axis, you can see that the graph would look different than the original. All right. And then for number three here, this graph is said to have origin symmetry. Why? Because if I rotate this graph about a stick protruding from the origin and perpendicular to the plane, and rotate that stick that connects to the graph 180 degrees, the graph will appear the same as the original. So in that case, it's said to have origin symmetry. All right, let's look at some examples. Suppose given each graph below, tell whether the graph is symmetric with respect to the x-axis, y-axis, or origin. All right, let's take a look at number one. We can see that if we rotate number one, which is this curve right here, if we rotate it about the x-axis, the graph will look different than the original. Whereas if we rotate it about the y-axis, the graph will look identical to the original graph. So this graph here, number one, is said to have y-axis symmetry. All right, for number two, we can see that this circle here, if we rotate about the x-axis 180 degrees, the graph will look the same as the original. Also, if we rotate this graph 180 degrees about the y-axis, the graph will look the same as the original. And if we were to, make a stick that protrudes perpendicular to the plane here, or the coordinate plane, and rotate that stick 180 degrees, the graph would look the same as the original. So in this case, we've got x-axis symmetry, y-axis symmetry, and origin symmetry. Right. For number three here, we can see this graph, it does not have x-axis symmetry. So if I rotate the 180 degrees about the x-axis, the graph will look different. It does not have y-axis symmetry because imagine this graph being rotated rotated about the y-axis 180 degrees, then this arrow here that's going up would go up this way. So it's not going to appear the same as the original. But it does have origin symmetry, because if we imagine a stick perpendicular to the plane and rotate that stick, which is attached to the graph, and rotate it 180 degrees, like clockwise or counterclockwise, the graph would appear the same as the original. So therefore it has origin symmetry. And let's do one more. We can see that this graph in number 4 here, this curve, does not have x-axis symmetry. It does not have y-axis symmetry. It does not have origin symmetry. So this graph has no symmetry. So we can see from this that sometimes a graph can have more than one symmetry, or it can have one type of symmetry, or it can have no symmetry. All right, let's move on to another example. How do you test a given equation for symmetry? All right, here's a procedure for testing an equation for symmetry. An equation is said to have x-axis symmetry if, when you let y become negative y, and then see if the original equation results. If it does, then it has x-axis symmetry. To test an equation for y-axis symmetry, we let x become negative x and see if the original equation results. To test for origin symmetry, we let x become negative x and y become negative y and see if the original equation results. So let's look at this example here. We're given this equation and we want to test to see if it has symmetry, any of these types of symmetry. So let's first test x-axis symmetry. So for x-axis symmetry, based on the above, we're going to let y become negative y. Okay, when I let y become negative y, so that means anywhere in the equation, everywhere I see a y, I'm going to change it to negative y. And you can see that when we do that, we'll get negative y equals, this is not the same as y. See that? It's not the same as y. Negative y is not the same as y. So immediately here we can see that there's no x-axis symmetry because we get a different equation. We pick up a negative, so there's no x-axis symmetry. Because we can't get this back to the original equation. All right, let's test this time for y-axis symmetry. For y-axis symmetry, we're letting x become negative x. When we let x become negative x, it means everywhere in the original equation where I see an x, I'm going to change it to a negative x. So I got y equal 3, and I'll put a negative x instead of x in parentheses, and then a negative x squared plus 9. And let's see what we get when we simplify this. We're going to have negative 3x. Now, negative x squared will give us a positive x squared. Plus 9. And you can see that this equation is not the same as the original. the original had a positive 3x over x squared plus 9. So they're not the same. So this, we can say therefore that there's no y-axis symmetry. All right, now let's check origin symmetry. For origin symmetry, we just say let x become negative x and let y become negative y. Now, we already saw the result when we let x become negative x. We came up with an equation, negative 3, well, let me take it slow. 3 negative x squared plus 9. And now, if I also let y become negative y, I get this, right? And now simplify this and see if we result in an equation that is the same as the original. And hopefully you see how I let y become negative y and I let x become negative x. Okay, so now I'm simplifying this. So get negative 3x in the numerator. Negative x squared, we said, is negative x quantity squared is x squared plus 9. And then on the left-hand side, we got negative y. And then when we simplify this a little more, say by multiplying both sides by negative, or just moving this negative over, or dividing both sides by negative, you can see that we're going to have y equal positive 3x, x squared plus y, which is the same as the original equation. Therefore, we can say that this does have origin symmetry. All right, so this equation has origin symmetry. I hope you found this video helpful. Like and subscribe. Math is order. That's what we feel. It's not just about numbers and symbols.